Hello everyone, welcome back to Introduction to Semiconductor Devices. So in the last week we were studying how the MOS capacitor works. We studied the electrostatics of a MOS capacitor in quite a bit of detail, and we've also explored what happens when the depletion charge changes, and when you change the gate voltage from accumulation to depletion to inversion and so on. While doing that, we have made a series of assumptions right at the beginning. We refer to that as the assumptions for an ideal MOS capacitor. It turns out that those assumptions are not strictly valid. They are broken many a times. So today we will look at two of the assumptions that are broken, and they have significant impact on the threshold voltage of MOSFET. So we will study that today. So to start with, if you remember, we have assumed that the metal and semiconductor Fermi levels are at the same point. That means the work functions are same. In other words, we define phi ms as a quantity. Phi ms, I'll write it here. So phi ms is a quantity which is the difference of work function in the metal and the semiconductor. So phi m minus phi s is equal to 0 for a ideal MOS capacitor. Okay, by the way, this is basically work function of a semiconductor. Right? So phi ms is 0. But in real life we use metals. Like for example, let's say we use aluminum. It's got a fixed work function. And what happens to the work function of the semiconductor? Well, it can change, right? It can depend on the doping density. We know that because the definition of work function is the amount of energy required to take an electron from the EF to the vacuum level free, to make it completely free of the semiconductor, right? So, of course, that depends on the doping density of the semiconductor. For example, if I define this, let's say there is a vacuum level. You have this, let's call it phi m, and phi s would be, okay. So please again note that this is work function and not the surface potential. I'm sorry for the unfortunate similarity. Okay. So now this is going to be equal to chi plus Eg by 2 plus phi f. Okay. So the entire thing, right? This is phi f. The top thing is from EC to vacuum level is chi, and this is Eg by 2. So we can calculate, the semiconductor's work function would be dependent on doping, and we can actually compute the phi ms. And it turns out that many times, or most of the cases, it is not equal to 0. So the assumption that the work function difference is the same is strictly not true. Okay. So what happens if you have a work function difference? So it turns out that, let's say if you have a situation like this where your phi m, the work function of the metal, is smaller than the work function of the semiconductor, electrons will be transferred over this barrier into the semiconductor. There's always finite probability of electrons getting transferred over this. Okay. At equilibrium, what happens is there is a probability this way and then there's a probability this way. They'll balance out, so there's no net transfer. But right now in the beginning, when you have EF of the metal substantially higher than semiconductor, there is a non-zero probability of electron transfer this way. So when electron is transferred into the p-type semiconductor, it recombines with a hole, and that results in reduction in the number of holes. Okay. So that is why even if you don't apply any voltage, you will end up getting a depletion. Okay. So here basically there are exposed acceptors. Okay. So the charge is going to be Na minus, right? The density, the negative charge associated with an acceptor which is ionized. Okay. So you have less of holes, and that's why you have this, depletion region. You also call it the depletion region, right? The holes are reduced in number, so it's depleted. Okay. So without any external voltage, we are having the semiconductor to be depleted. That is one of the consequences of having a non-zero metal work function. Sorry, non-zero work function difference. Okay. So, and also you see that there is a electric field in the oxide which is constant. Why does that happen? Because, well, you have negative charge here and there will be a positive charge on this side automatically because electron is removed. So on overall there's going to be electric field, okay, across oxide as well across the semiconductor. It's like a depletion. So this is what happens when there's a work function difference. You can have another scenario. For example, you can have a scenario where you have the semiconductor EF is somewhere here, and then you have a metal which is having EF here, right? This is also possible because we saw that if you take metals like platinum, they're going to have reasonably high work function. Okay, aluminum is only 4.35 or so, but platinum I think is much higher than that. Okay, so in that scenario, you will have electron transfer in this fashion. In the earlier case, electron transfer was this way. Electrons always move from regions where the Fermi energy is higher to the regions where Fermi energy is lower. Right? When you have electrons moving this way, you will see that holes are getting created here. Additional holes accumulate here, right? Because it's only at the surface this effect is valid. So because of that, the band diagram you could draw, and it might look something like this. Okay, so EF is still uniform because there is no applied gate voltage, but the semiconductor is already accumulated here, right? So either of these scenarios can happen, or it might happen that if your metal and semiconductor work function difference is very, very large, then it will really go to even inversion sometimes. Okay, so this is an important aspect that we need to study. So how do we account for this? Okay. So let's say you have this sort of a depleted semiconductor. What can you do to make it go back to the original state? Okay. So to do that, we can essentially apply, like for example, we have read on here, this is the depleted state. And we have said that whenever you apply positive gate voltage to the metal, it will move down, right? Positive Vg. If I apply a negative Vg, it moves up, the Fermi level of the metal moves up. So now what we can do is apply a negative voltage such that you pull the metal Fermi level up. Okay, so that will force the bands to come into the flat band condition. So this is basically, it's called as flat band condition. I mean, it's not very complicated, so bands are flat, that's it. Okay, flat band. So essentially, this was what we wanted initially, right? Because this is what we studied. In ideal semiconductor, this was happening at no applied gate voltage. But if you have a work function difference, then by default, I mean, there has to be certain applied voltage to go back to the flat band condition. Okay. So how much is this voltage? Well, the amount of voltage is going to be, you have this EFM, and then there's going to be EF of semiconductor. So the difference between them is going to be phi ms. Okay, so if you apply phi ms of voltage, then you can actually take the MOS capacitor back into flat band condition. Okay, so that is why we have considered this in the last week, where we showed that this is a threshold voltage for an ideal MOS capacitor. Why is it a threshold voltage? Well, I mean, we have derived a relation between Vg and phi s, and then we said that, okay, this is when the surface potential is equal to 2 times phi f, then it is going to be threshold voltage. So that's why this is ideal MOS capacitor's threshold voltage, but because of this difference phi ms, there is a correction to the threshold voltage. Correction to account for work function difference. This is going to happen. So we have the new VT. So it doesn't look so bad. So all we have to do is compute what is work function difference, metal semiconductor work function difference. Okay. There is another problem here. That is, this is essentially what was done in the beginning. When the technology was in the 60s and 70s, people used to use metal gates. So one of the consequences of that was, let's say you have an N-type semiconductor and you have a P-type semiconductor. Okay. The metal work function is going to be, let's assume, somewhere here. Okay, aluminum is about 4.35 or so. Okay, so metal work function is here. So for most of the semiconductor dopings, and for all the semiconductor dopings, if you look at metal, let's say aluminum, so if you look at aluminum and P-type silicon, the work function is always phi ms is negative. Okay. And in this case of aluminum and N-type semiconductor, because EI is going to be somewhere here, only for large dopings, the EF may actually go towards EC and then the phi ms might be positive. But in most of the cases, phi ms is negative again. So this is what you can verify. I mean, you can try to put in the exact work function of the aluminum and then compute and see what happens for different doping densities. You will see that it will be like this. So this is also another way of showing that. So here is the substrate doping on the x-axis and work function difference on the y-axis. But the various things will come to that. The first thing we want to notice is when you have an aluminum and P-type junction, or aluminum and aluminum gate and then P-type substrate, the phi ms is turning out to be in the range of -0.8 to -1 or so. Okay. So it's quite large. Okay. And for N-type case, it is negative for most of it. Only when you go to 10 power 19 or 20 or so, then this becomes maybe positive. Okay, a small positive. So why is this important to us? Well, one of the useful implications of an ideal MOS capacitor is that when you have this quantity here, right? This is essentially VT of an ideal MOS cap. So VT of ideal MOS cap is comparable in magnitude. Magnitude for NMOS and PMOS. Why? I mean, take a substrate of similar doping, 10 power 15 P-type, 10 power 15 N-type, and you compute the VT. It will turn out to be same. Okay, so there's a certain amount of symmetry in the type of transistors you can make. Whereas if the moment you put a phi ms is a large negative voltage, then the VT will shift. For example, I could draw this axis, voltage axis. There's a 0, so I'll have a, let's say, VT N naught and minus VT P naught. So basically what I'm trying to say is this difference of VT from 0 is going to be symmetric. Basically this is going to be similar, comparable for ideal MOS capacitor, right? Because QD is going to be comparable and phi s is going to be, so the surface potential is going to be comparable. So you're going to have a symmetric VT. But the moment you add a phi ms because of, let's say, metal, the whole VT shifts down. If you're adding an aluminum gate, we are seeing that for most of the voltages, it is basically negative. For N-type, it is going like this. For P-type, it's going like this. So the VT is going to now become something different, right? So VT might be somewhere here. VTN, and this might be some VTP, okay, minus VTP. So NMOS has a very small VT maybe, and PMOS might have a large negative VT, right? So they're not comparable in magnitude. Okay, and this has actually significant implications. We like the VT to be comparable, okay? Because in our technology today we call it, actually you might have heard about it. We call it complementary MOS technology, CMOS we call it, CMOS technology, which essentially has NMOS transistors and PMOS transistors fabricated on a single chip. And we like both of them to be sort of complementary devices. That means the drive current, the threshold voltage, everything is symmetric. It is easier for us to design circuits when they're complementary. And there are also some very nice, interesting circuit implications for this. So we like this to be complementary. But if you just have a pure metal, it's not so. Okay? So you might ask, why was this done in the beginning? Well, I mean, that actually, to be honest, there's only one type of technology, which is NMOS, which was available in the beginning. And the threshold voltages were quite large, so it didn't really matter how much the small difference in the work function was. But over time, the supply voltages, we used what is called a scaling of voltages. So in the 1960s and 70s and maybe even 80s, the chips used to work at 3.3 volt technology, okay, 3.3 volts and even 5 volts in the beginning, and then 3.3 volts. But with time, we started reducing the supply voltages. So then the electronics chip started working at 1.8, so 2.5, 1.8, 1.1, and so on. So the supply voltages were gradually reduced from the 70s and 80s to present day. The reason this happened was it has some benefits. We will talk about it when we discuss the scaling of MOSFETs. Okay, but as you go to lower supply voltages, it became important to realize symmetric sort of a work function. And the way this was achieved is by replacing metal with what is known as polysilicon. Okay, so metal replaced by highly doped polysilicon. Okay, so this has some benefits. We will discuss that in a moment. Okay, so because it's highly doped, it behaves like a pseudo metal and it can be used. Okay, so how does polysilicon work? So what we do in this case is, let's say you have the same p-type substrate resin. Okay, there is an EF. What if I use a P plus doping for my gate? P plus poly and p-type. Or I could use N plus poly. I mean, N plus means EF is close to EC. P plus means EF is close to EV. Sorry, I'll take an N type here. Okay, N type, and then this is N plus poly. Since it's highly doped, from energy, we can assume for practical purposes is at EC or EV. So now you'll see that the work function difference is quite small, correct? So because of that, if you see here the other curves, if you have an N plus poly on N type silicon, it's increasing like this, and if you have P plus poly, it is decreasing like this. So whatever you do, if you have a certain amount of symmetry here, this if you take as a 0, phi ms is 0, there's a certain amount of symmetry with the way the phi ms is changing. Okay, and that has very good, properties, because if you have comparable dopings, then your VTs will be comparable. This was not the case with aluminum, you remember? So you see here, if I take my aluminum at this doping, when you increase it, it's phi ms was increasing here, but for the p-type case, substrate it was decreasing. So it's actually having opposite trend. Whereas if you use polysilicon gates, they sort of have symmetric trends. Okay, so I'll say that phi ms is symmetric about phi ms equal to 0. So this was useful, and that's why slowly by 90s, late 80s and early 90s, we started using polysilicon gates instead of metal gates. There were also many other technological issues that we won't get into today, but it was useful to actually use this. You can also use the opposite condition. It has some benefits. For example, instead of using, if you have a p-type substrate, I'll use an n plus poly. If you have a n-type substrate, I'll use a p plus poly. I can use that also. That combination also I can use. Okay. So if you use, what happens? If I use p-type substrate and n plus poly, or n-type substrate and p plus poly, use this combination. If you do, what happens is you'll see that again the difference is almost like close to band gap. Okay, that's why you see here the phi ms. If you have a p plus poly, that means you're using poly to be p plus, and you're having an n-type semiconductor. Yes, right. So phi ms is basically positive for all doping actually. Right. That's why you see that it is sort of going in this way. As you increase doping, phi ms is increasing. Eventually, it will come to 1.1 eV. That's where the band gap is. Right. Similarly, if you use the opposite case, n plus n p-type silicon, you'll see that this is increasing. Okay. So these numbers are strictly, this graph is taken from, adapted from one of the references. Okay, I should have mentioned it. The textbook has one graph. Okay, adapted from, I don't remember the chapter, you can look up. Okay, adapted from Neiman. Okay, the only issue is that here, these are also including additional correction factors. Okay. So anyway, for now, this is a good enough graph to explain the behavior of how the polysilicon works. Okay. So once we do this sort of a thing, we have a large phi ms, but it is useful in certain situations. I'll let you analyze this by, you can actually in a nano hub, we will show you that you can use aluminum gate or n plus gate or p plus gate. I will let you analyze the usefulness of this situation, wherein you use the opposite type of poly. If for example, p type and n plus poly, what is the advantage of this? It looks like phi ms is either large negative or large positive. So why is it useful? I will let you analyze this. Okay, please run it and we will discuss it some point down the line. Okay, all right. So this is the theory part of it. Let's try to solve one problem. So the problem given to you is that determine the metal semiconductor work function difference phi ms for a given MOS system and semiconductor doping. Okay, so the aluminum silicon dioxide junction is given to you. Okay, with a phi m. Okay, this is S. Okay, and asked to calculate the phi ms. Okay, fine. So there's a small change in the notation here. This is taken from the textbook, so please you can go back and refer to it. So the textbook uses a slightly different notation that if you have a, this is what type of gate, aluminum, right? Okay, so aluminum, let's say this is here EF of M, and then you have, let's say EC, EV. Okay, so when we say that it's phi m, right? So basically there's an oxide in between. So there is an oxide here, right, in between. So let's assume this is your oxide EC, and this is your oxide EV. The way textbook defines phi m prime, right? Phi m prime is this quantity. The difference of metal work function with the EC, not the vacuum level, but EC of the oxide. Similarly, chi prime, it is defining as this. Remember, original chi was the distance of EC from vacuum level, but now we are defining chi prime as something from EC edge of oxide. Okay, so this is given to us 3.25 volts, and this is given to us 3.2 volts. Okay, so that's why I have drawn EF to EC to be slightly lower than EFM here. Okay, so now what is the work function difference, phi ms? Well, for that you need to find what is this work function of the semiconductor. Work function of semiconductor will simply be you have the EI, and it's given to be a p-type semiconductor, Na doping, right? So this is Na of 10 power 15. So there's going to be some, okay, I should do it with maybe red. This is my EF, right? So I need to find out what this distance is. Okay, so I'll call this as phi s prime, which is simply going to be chi prime plus Eg by 2 plus phi f. So this is going to be 3.25 plus 0.56 volts, which is Eg of Eg by 2. So 1.12 divided by 2, so that's 5.56 plus what is phi f? Well, it's 10 power 15 doping. So using our standard calculation scheme, approximate number is going to be 60 millivolts times 5. So that's going to be 3.25 plus 0.56 plus I would say approximately 0.3. Okay, you have to, it will be slightly, I mean, in fact, this for the exact answer turns out to be 0.288. Having done so many times, I remember this number. Okay, you can check it out. So now phi ms is going to be simply, where should I write it? So here, phi ms is going to be simply 3.2 minus, what is this quantity? 3.25 plus 0.56, so 3.8, 3.7, 81, 81, 81. So is it, this will be roughly 4.1? I think it should be roughly 4.1. Okay. So minus 4.1. You just verify this carefully. That should be roughly 0.9 volts. Okay. This is the metal work function difference. Work function difference with the minus 0.9, sorry. So this is the work function difference for aluminum and p-type semiconductor. Okay. So is it consistent with what we have studied? So 10 power 15. So this is the graph mentioned, right? So 10 power 15, yeah, 10 power 15 p-type substrate, and then, oh, this is metal. Aluminum is somewhere here, right? Aluminum is here, yeah. Yeah. So aluminum and 10 power 15, this is somewhere here. Okay. So minus 0.9. So yeah, what we're getting is approximately there. Okay. All right. So this is how you can calculate the work phi ms, work function difference, and that will modify your VT. Okay. So this is one form of non-ideality. There is another form of non-ideality that we would like to study, which is basically the formation of traps in the oxide. So in the assumptions for an ideal MOS capacitor, we said that there are no traps in the oxide, and the interface between silicon and silicon dioxide is perfect. You know, there are no traps there as well. But again, this is not a very accurate assumption. There are certain limits to it, because always when you form an oxide in any process, there is going to be some traps. And even interface, there are going to be some dangling bonds that we discussed some time back. So these traps, basically I can represent them as, you know, some positive or negative charges. So basically traps are distributed in energy and also position. Energy and position, right? They have some distribution. They can be in different locations. For example, there could be some distribution of trap plus minus. They could be on interface at whatever energies, right? So this is going to be there. So if you have some traps, they're going to hold some charges. You know, if they're fixed traps, they're going to hold a charge permanently. So how will that impact the VT? Okay. Suppose if you place a positive charge, let's say somewhere in the semiconductor here, okay, that positive charge will have a field which will drive the holes away. If you're having a p-type semiconductor, it will drive the holes away. And without any applied gate voltage, you might have a scenario where there is depletion. This depletion created by fixed charges, okay, or interface traps. You know, fixed any, you know, it can be fixed trap, oxide traps, or, you know, oxide means in the bulk of the oxide. Interface means right at the interface between silicon and silicon dioxide. So you can have either variety of these things. Okay. So when you have such a variety of charges, then you will have depletion, or sometimes if you have a negative charge, you can have accumulation. That's also possible. So it becomes a very tricky thing to analyze it, in detail what exactly is happening. So one of the we can make an assumption to account for this. Okay, so we will define what is known as an equivalent interface charge. Okay, it is it's assumed to be at the interface between silicon and silicon dioxide. Let whatever be the distribution of the charges in space, we will assume that all of it is at the junction, and there's an equivalent charge. We can try to compute so that it has a net same effect on VT. Okay, so this equivalent charge, I mean, there are experimental techniques by which you can determine how much is this, but we don't need to know that. For us, for our practical purposes, we will say that there is this interface charge, and it is assumed to be positive. Okay, positive right now. Okay, if your equivalent charge is given as QI, that's the interface charge. If it is given as minus, let's say some charge, coulombs, then we have to put that minus. So right now in this expression, this is positive. Okay, here. So once you have it, your VT will be modified. How does it get modified? Well, the expression is this. You have the ideal MOS capacitor, and then there's an additional correction because of this. Okay, so this set here is basically corrections for the non-idealities, right? Non-idealities. Okay, so this is also called as sometimes work VFB, flat band voltage. Okay, so flat band voltage. If you apply this to the gate, then your bands will be flat, right? And the rest of it is the ideal MOS cap. Okay, so now let's just analyze quickly. Let's say if your QI, equivalent interface charge, is positive. Okay, if your QI is positive, what should happen? Implies p-type semiconductor is depleted, right? If you have a p-type semiconductor, it will drive the holes away. P-type depleted, right? Okay, if your p-type is already depleted, it's easier to create inversion, so VT is lowered because of this. Okay, implies VT reduces. That's what is happening because QI is positive, so overall VT will reduce. Formula is telling you, and physically also once you deplete it, otherwise the gate had to deplete the semiconductor and then produce inversion. But now already some part of the job is done by the fixed charge, so already it's been depleted, so you can quickly go to inversion. Okay, or if the QI is negative, p-type will have accumulation, right? So now implies this has the overall VT has to increase because you have to push the accumulation charge away and then deplete it and then invert it. So the VT increases, the magnitude of VT increases, right? And you can analyze the same thing for the NMOS transistor as well. We can find out what that is. Okay, so I'll leave it to you leave that as an exercise. Okay, so this is how your traps behave. Okay, so let us quickly try to solve a couple of more problems, and with that we can conclude our discussion on the non-ideality. So far, we will only discuss these two. Later on, we'll just mention the gate oxide leakage. Okay, so let's take one more problem wherein we want to find out what is the flat band voltage for a MOS capacitor which is having a p-type substrate, let's say. Okay, so I will not solve this problem. I'll quickly tell you how to do this. Okay, so you're asked to calculate the flat band voltage. Remember, flat band voltage is VFB, which is simply phi ms minus QI by Cox, where your QI is the equivalent charge. Okay, well, okay, you'll have to live with my definitions. QSS prime is basically QI in my definition. Okay, we are taking material from various books, so each book uses a slightly different notation, and it becomes it can be confusing, but just note that QSS prime that Neiman uses is essentially equivalent positive charge. Okay, and let's solve this. So it's you have an N plus polysilicon gate, and then you have a p-type substrate. Okay, so N plus polysilicon gate. So I'll say that the EF here is at EC. Okay, EFM is at EC. because it's highly doped. Okay, I'll assume that. What about the P type? Well, you have this EI, and then there is this EFM, sorry, semiconductor, whatever it is, right? So how much is that? For this particular doping, I need to find out what is this distance. This is phi f, that is going to be 60 millivolts into 6, so 0.36 volts, phi ms, sorry, this one. So phi ms is going to be, I'll take it by Eg by 2 plus phi f, that's going to be 0.56 plus phi f, sorry, phi f is already known to us, 0.36 volts. So 36 plus 56, it is 692. Okay, so 0.92 volts is your work function difference. And we need to find out what is, okay, Cox. Qi is already known to us, Cox. Cox is simple. Cox is epsilon oxide divided by thickness of oxide. That is 3.9 into 10 power 8 into 8.85 into 10 power minus 14 farads per meter, farad per centimeter, divided by 20 nanometers. So 20 nanometers, you need to write it in the units of centimeters. So 20 into 10 power minus 7 centimeters. So this will turn out to be what? Well, okay, I have done it multiple times, the same problem. So basically 8.85 into 3.9 will turn out to be 34.5 into 10 power minus 7 divided by 2. So that will be 17. So 17, no, not 7, but divided by 20. Okay, so yeah. So 172.5 into 10 power minus 9. So yeah, it should be something like this. 1725 nanofarads per centimeter square. This is your Cox. Okay, I mean, verify. 170 will be 340, 2.5 will be 5. Yeah, correct. It should be correct. Okay. So now with this information, you can easily compute what is VFB. VFB equal to phi ms was 0.92 minus Qi was 5 into 10 power 10. Remember, this is the charge density per centimeter square. We need a charge. So this is one important thing you need to remember. 6.10 power minus 19 divided by 172.5 into 10 power minus 9. I don't know, something will come out, some x. Well, I'm sorry, this is not cross, some number. Okay, what is this number? You calculate. Okay, so this is how you solve this problem. Remember, you have to multiply the charge by the electron charge here. You should remember this is 3.9 and this is 10 power 14 minus 14. This is important. This has to be expressed in centimeters. So these are all the careful precautions you have to take to get the exact numbers. Okay, so you will compute that and you'll find out some numbers. Okay. So this is how you solve. This is again example 10.3. You can go back and refer and then make sure that your answers are correct. Okay. And just one last example. What is the threshold voltage? Okay. Now with aluminum gate, okay, P-type substrate. Oh, this all of it is involved here. Okay, fine, good. So basically your VT is going to be phi ms minus Qi by Cox. Please write it multiple times so that you will not make a mistake in this, plus 2 phi f. Okay. The first thing we need is basically phi f. Phi f is, by now we have done it so many times, phi f is 60 millivolt approximately into phi. So that will, I mean, this will be, the exact answer I said will be 0.288. Okay, 288 volts, fine. Okay, so now once you know that, why is this useful? If you know this, you can calculate the width, right? Because we need to calculate charge. QD is going to be Q times Na times, it's NMOS or PMOS? Yeah, NMOS. So this is going to be minus here. Okay, minus QNA, and then this is going to be the width, whereas the width will be given by square root of 2 epsilon silicon divided by Q and A times 2 times phi f, because we want the width at the threshold. Threshold it is 2 phi f. Surface potential is 2 phi f. So at 2 phi f you take the width. So that will be some W naught. Okay, so let's call this as, you solve this and you find out one, whatever that is, W naught. Okay. So once you do that, you find out what is QD. Okay. Simply it's going to be 10 power 15. Huh? So 1.602 minus 1.602 into 10 power minus 4 into W naught. This will be second step. You finish this and you'll get this number 2 answer. This QD you'll get it. Okay. What is COX? After some point it becomes plug and chug, right? TOX. TOX is 12 nanometers. So the same story, 3.9 into 8.85 into 10 power minus 14 divided by 12 into 10 power minus 7. You will get some answer. I'll call it C naught. Okay. Let me call this as 3. Okay. So once you know this, what else do we require? We require to know what is phi ms. Okay. What is phi ms? Phi m minus phi s. This is aluminum gate and p-type substrate. Oh, we did this. We did this already. Let's go back. I think this was the case of aluminum and p-type doping with 10 power 15. So it was 0.9, minus 0.9. Okay, so this was minus 0.9 volt. Okay, so this is the fourth step. You finished. So put 1, 2, 3, 4 into the main equation. Substitute 1, 2, 3, and 4 for to calculate VT. It will be some number. Okay. This is going to be minus 0.9. Okay, no, I will not be able to get it right. I need a calculator to do this. This is going to be 10 power 10. Okay, so 10 power 10 is there. So this will be 1.6 into 10 power minus 9 divided by, okay, yeah, C naught minus, yeah, you just calculate all this rest of it, okay. This will be plus because there's some here, right? This is going to be 1.6 into 10 power minus 9 into W naught by C naught plus 0.288. So into 2, 6, 7, 576 millivolts, I think. Okay. So yeah, please do this and then verify. This is how you compute. Okay. So yeah, we now looked at how the non-ideal MOS capacitor should work. Okay. With that, we will stop this lecture today. And in the next lecture, I will discuss briefly about what is CV characteristics and how do we understand CV characteristics. Okay. So and then we will also show you some example problems and then discuss various dependencies of the CV. And with that, the MOS capacitor discussion will be complete. So we'll do that in the next 1.5 hours. Then we'll have a brief demo on the nano hub. Thank you so much for your attention. Good luck.